Hello, everyone. Title of the talk, the Universal Digital Twin, Accessing the World of Chemistry. Let's start. Okay, before I actually talk about content, I would like to tell you who has produced this work. And one group of people is CMCL. This is my startup company in Cambridge. And the other group sits in Singapore and is part of CARES. CARES is the University of Cambridge laboratory in Singapore, and we work with Nanyang Technological University and National University of Singapore on topics that are related to Singapore. And so the Universal Digital Twin is part of our program on decarbonization. What you see to the left here, that is Marina Bay Sands, and have a careful look because it will turn up later in the talk. Okay, so right, off we go. So today I'm talking about knowledge graphs, and this is a technology that we use for our project, Universal Digital Twin. So that's the mother of all digital twins, so to say, which we call the World Avatar Project, formerly known as the JPark simulator, because Jurong Island Chemical Park is a big consortium of chemical industries, which we aimed to make greener, having a lower CO2 output. Right, off we go. Knowledge graph, what is it? I guess many of you would know what a knowledge graph is, but for those who are not so familiar with, I can tell you, you're using it every day. So in 2012, Google has introduced what they call the Google Knowledge Graph to represent these information boxes that you see when you type in the question into Google. Okay, and that's what's behind it. Okay, it's basically organizing data in forms of triple. So, for example, Barack Obama is married to Michelle Obama. So, subject, predicate, object. But that is not only done with data, it's also done with concepts, and these concepts in turn are used to define what these data points are. So this is called knowledge graph. Now, so we, oh, hang on, something happened. So sorry. So we use this concept for the World Avatar Project, and that is a slight extension of what you've seen now. It's a dynamic knowledge graph. That means that this graph is constantly changing, and it's a representation of the real world. I mean, like when we say world, we just mean everything, not just the planet Earth, but everything that is conceptualizable. And so that forms a general purpose and all-encompassing data storage and modeling framework. And it contains concepts and data that describe the real world and that are operated on by computational agents. So what does it look like? So here you see it. So the green area here is a bit like your hard disk, and the red area is a bit like your memory. So we have concepts and instances. So that means we have an ontological representation of data. We use the concept of linked data, so all these things are connected. We have a system of agents, and please note that these agents are not only software that act on the knowledge graph, they are also part of it. And this is a very important aspect of it. So it's a fully enclosed system. And the beauty of this construction is that this distributed directed graph is unambiguous, it's connected, it's scalable, it's distributed, accessible, multi-domain, interoperable, and that is something we want to use specifically, and is evolving in time. So what ontologies are there? And I've promised you I want to, in this talk, sort of concentrate on the world of chemistry. So some of you, I've just listed a number of ontologies that have been used in the area of chemistry. Some of those are very well known, for example, the GBI or the ChemInf ontology. So these would be used for molecules, but then there's also a reactions description. Okay, some of these acronyms you may have seen. Then also equipment ontologies. So the bottom line, there is quite something there. However, as I am a chemical engineer who comes from the combustion side, we found that for us, these ontologies weren't so useful. So we could use some of the concepts, but we had to create some ontologies of our own. And one is OntoPESScan. This is an ontology that is able to store computational quantum chemistry data. We have OntoSpecies. This stores species identifiers, entropy of formation. And then we have OntoKin for chemical kinetics and thermodynamic data. We also connect to Wikidata to access the wider community chemical database that is in Wikidata. Right, so just a quick run through. So OntoPESScan, that's an open repository containing results from quantum chemistry calculation. So you can query this with the Sparkle queries, for example, or here we have a user interface that you can see here that lets you visualize the molecules and also shows you information like frequencies and basis sets and stuff like that. So then we have OntoSpecies, again, open repository that contains species identifiers like INCHIs, MARS, CAS numbers, PubChem, CID. It contains weight, charge, enthalpy of formation, bond and geometry information. And because it can be linked to OntoPESScan, we get a unique species definition that allows us unambiguous linking between these ontologies. Okay, so this the link to OntoPESScan, to the computational chemistry for each species, allows you this uniqueness representation that you don't have if you use SMART or so. Okay, and then we have OntoKin. Again, it's an open repository for chemical kinetic reaction mechanisms. I'm not sure if you're a proper lab chemist, you may not be familiar with that, but these mechanisms are also used in atmospheric chemistry. They contain elementary reactions because it's gas phase and can be very complex, can be up to thousands of elementary reactions long, okay? And OntoKin, for example, allows you to compare different mechanisms, to look at here rate constants and enthalpy of heat capacity and enthalpy of formation, for example. Right, okay. So these are the ontologies. Again, OntoKin, just to give you an idea, if we zoom in, so you have a reaction mechanism, okay, you have a chemical reaction. It can be a gas phase reaction or a surface reaction. The gas phase mechanism has a gas phase. This, if you go down, consists of chemical species. Each species has an element. There's an element number. Then there is a thermal model and a transport model for the species. Then it has the mechanism has reactants and products. And each reaction can either be a Arrhenius reaction, fall-off reaction, Landau-Teller reaction, and then there's a rate coefficient, and so on. So this gives you an idea of the complexity, and here this figure basically shows how it's all connected. So for example, this is water and it's hydrogen. So water appears in mechanism 1. So it has an IRI, as unique species identifier, a thermal model, as quantum calculation, okay, that refers to this thermal model, and then that points over to the corresponding quantum calculation, and then the next species, hydrogen, and so on. And so it's all connected, and here you can have different level of theory. So depending, for example, you can produce mechanisms that are consistent with respect to level of theory. It's being used for the data that is derived from the quantum chemistry. Okay, so this is how this is connected. Now we're at the moment also working on new ontology, and one is the potential energy surface scan ontology. Here we're looking at an ontology that allows us to describe computational scans of a variety of potential energy surfaces, for example, like bond, angle, and torsion. This is what you see here, bond, angle, and torsion. And so this is linked to ontospecies, to uniquely define molecules and fragments along the surface. It can unambiguously define scan coordinates for potential energy surfaces. It's linked to OntoCompCam, so that each point along the surface has an associated quantum calculation. So, and the retrieval of energy and geometry data via OntoCompCam is possible, and this enables us to automatically to fit force fields for molecular dynamic simulation. This is why we're doing it. So another ontology we're developing is OntoMOPS, where MOPS is a shorthand for metal organic polyhedrous. So the idea here is that we describe macromolecules in terms of their building blocks, and doing that, we hope, using a mix and match approach to derive potentially new molecules. These molecules are very important. They're used for basically sheltering other molecules. So, for example, in homogeneous catalysis, it's been used in coatings, quantum computing, batteries, and so on. Right, okay. So these are the ontologies. And the next question is, how do you extract information out of the knowledge graph? And for that, we've published a paper that came out this year. So it's a question answering system for chemistry. And so this webpage provides an easy access to our knowledge graph, the world avatar, and it uses natural language tools. And the idea is that I give you a quick introduction on how this works, okay? So the first question is, why do we need sophisticated natural language processing agents to query a knowledge graph? So why is that the case? Right, okay, I can tell you why it's the case, because the technology that you use is called Sparkle, and that is a bit cumbersome and requires specific knowledge of ontology. So how do you do this stuff in Sparkle? So first of all, you need to know which ontology you have to use in order to formulate your query. And the query is, what is the molecular mass of ethanol? What is the molecular mass of ethanol? So the Sparkle protocol. So you start with Sparkle syntax. So it has been designed to be similar to relational database query languages, such as SQL. So we start with the select statement, where we list variables that are that at the end of the query will have values of the things we are looking for. So this is the value, the molecular mass. Okay. So the query depends on the ontological representation of data. This is where it becomes tricky, because it means you need to know what the ontology looks like, whether it's ontospecies or Wikidata. Okay, so right, so this is the ontospecies graph, and so hang on. Right, so the first thing we need to do is to find ontospecies entry that corresponds to ethanol. Okay, then we can do this by using species has name property and matching it with the user provided ethanol name. Okay, so here we go. So the body of the Sparkle query that does that matching is shown here to the left. So having found a unique ethanol species entry in the graph, we can explore it's other relationships to find the property we're after. So in this case, we will use the molecular mass property to find the molecular mass concept and the subsequent value. So, okay, let's do this. Okay, here we go. And that gives us the corresponding value. So this is quite complicated and it requires experts. So ideally, we want to have a better entry point. So how do we abstract the query process from the ontological representation of data? Okay, so we do it in the following way. So we use the agent family that help us to produce this Sparkle query. So first of all, we need to understand the topic, question classification, named entity recognition, ontology lookup, and then the Sparkle formulation that gives us the number. So we start with the question, what is the molecular mass of ethanol? Okay, so the topic agent basically puts these words as an input and then returns probabilities which of the specific ontologies are the most suitable to answer this question. Okay, and here we use bag of words and then derive this probability. So here we get onto species and we look at that ontology. So that goes into the next, as an input into the question classification agent. And the question classification agent assumes that there are a number of different types of questions. For example, the item attribute query. So this is molecular mass of ethanol is one attribute of ethanol, or a batch attribute query, molecular masses of hydrocarbons, so that you here the answer is a whole list of things. Or a rank query, rank the molecular masses of hydrocarbons. Okay, then we have an order implied in that list. Okay, or an about query, what is ethanol? So it's a thing. Okay, so now in this case, what is the molecular mass of ethanol is query clearly an item attribute query. So now we know the type of questions. Okay, so now we need to understand what goes into this question. And for that, we know that the item attribute query contains species and attribute, and now we have to identify what is the species and what is the attribute in this sentence. Okay, then the next step is the ontology lookup agent. Now where we know species ethanol, attribute molecular mass, we have to find the IRIs for these two things. Once we have that, we can then use the last step, the Sparkle construction agent, and off we go. We can now query the knowledge graph. Okay, and we construct this query and execute the query and get a result. So here is the Marie, a snapshot of the Marie page, and what is the molecular mass of hydrogen. We have formulated a number of sample questions, and that works, but it's still work in progress. It's not, there is still work to be done. Right, okay, good. That's that. I would like to show you a couple of use cases that all act on the knowledge graph. So whatever I show you, I don't show you disconnected projects, I show you one and the same thing, okay? So this is, I told you I'm a combustion man. So one question we are interested in is synthetic and biofuels, and one of the fuels is called PO3, polyoxymethylene dimethyl ethers of length 3, okay? So they have a repeatable unit. And so this is a carbon neutral fuel, easy to fit in the current fuel infrastructure. So, so we would like to understand, we want to have a computational model that tells us how this thing combusts, okay? And there are computational mechanisms that write out all the elementary reactions. And this is what you see in the literature. And, but question is this good enough? Okay. So what we want to do is automate the model development. So in future, you just put a molecule in there and like magic, pop, a chemical model comes out that is already calibrated to all the experimental findings that exist. And for that, we need to do certain operations. For example, sensitivity analysis. So there is a local and global sensitivity analysis. And from a mathematical point, this is how it's written, okay? So ether is any derived quantity. So there is a process condition and a model parameter. So this could be the reaction rate. This is the process condition that tells you, for example, what equivalence ratio, whether the fuel is fuel rich or whether it's more oxygen in it, okay? And then here we also use a perturbation, okay? So note the difference, here is a tilde, and we can perturb the ith representation of the model perturbed in the jth direction, and then we can make this, we can modify this perturbation, and then we can look at the maximum over all these points in the process condition space. So this is classical. And once you have done the sensitivity analysis, you can then reduce the number, the vector of theta, and then the classical step then is to introduce a new variable, that's eta dash, which is basically a log, a normalized log variable, which you then use to minimize this objective function, which basically in this case are ignition delay times plus flame speed times. And you see here, we look at the experimental value and the model value, and we want to minimize this distance. And here again, experimental value versus model value. And then we use this value here. Great. So if you did it by hand, you'd go through the following steps. You have a chemical model, starting mechanism, experimental data for ignition delay times, laminar flame speed. You have a simulation, and this simulation is managed by a software we call MODS. It's called Model Development Suite. It's one of the CMCL products, and then kinetics and Cantera are basically partial differential equation solvers, and one for the ignition delay time and one for laminar phase speed, and then you do a sensitivity analysis and then global search and local optimization. This is the hand setup. So what we want to do is having everything working in the knowledge graph automatically without human input. Okay, so that's the key point. This is what we really want to do, some sort of intelligent behavior of model calibration. So, and how do we do this? For chemical model, we have OntoChem, experimental data, we have produced OntoChem experiment. I will quickly describe that later. Then we have agents, that MODS is sort of the optimization agent, and then we have the agent for kinetics and for ignition delay, and Cantera for the flame speeds, okay? And there are steps, and these steps are basically creating the corresponding MODS files, and that all needs to be woven into the knowledge graph, okay? And this is how I show. So in step one, you basically use information onto chem experiment, onto species, onto kin, into the knowledge graph. You then have automated agents that invoke the MODS agent, that calibrates the mechanism, make sure that the line goes through the dots, okay? And this calibrated mechanism is fed back into the knowledge graph. Okay, so I'll go through the slides a bit quicker. So this is again an ontology representation for, in this case, for experiment. So we have some bibliographic data, and then we describe the apparatus, different data groups that come out of this apparatus, and then we use different properties of the components that we have included. How does it all link together? So the two connections between OntoChem experiment and OntoSpecies are given by has preferred key. This is what you see here. And has unique species IRI. This is an onto species. So this is how we link this state. Right, so now there are different templates. I don't want to go through the details, but one thing I would like to mention, so this is the MODS template, that is sort of the agent that does the optimization and the sensitivity analysis. And because this is a longer, it is not a task that can be done instantaneously, this agent is sort of divided in an asynchronous watcher and a worker. And so the worker lives on a high performance computer and the watcher can live on any PC really. And sort of the watcher starts the worker and observes through HTTP the status of the process. And once it's finished, it takes the information of the high performance computing and then passes it back on to the knowledge graph. Okay, so this is a very hardware independent approach. Okay, so, and this is an intermediate step. This is file creation. Imagine you look at many different process conditions, and at the same time you want to vary your parameters in this process condition space, in the parameter space, which gives you many thousands of model evaluations, and MODS helps you to organize it and keep it all under control. Okay, so you have a coordination agent, so that requests mod sensitivity analysis. Okay, so that starts and then it gets the information out of the knowledge graph and returns mechanism and file and experimental data, and then it passes this information on back to the coordination agent. Then there's a calibration step, that's the MODS calibration agent, and then it communicates with the knowledge graph, gets information back, does the calibration, writes the optimized mechanism back into the knowledge graph, and basically it tells the coordination agent it's all done. Right, and these are just snapshots of results. So what you see here is a sensitivity study of the most important reactions. And this was for, the first one was the ignition delay times. And here you see it for flame speeds. And so this is an example of the mechanism calibration. That's actually a two-step procedure. Okay, so we start off with 10,000 Sobol points. Okay, not sure each of you have heard about Sobol points, but Sobol points are discrete measures that have a uniform distribution. I'm not sure that has helped you a lot, but imagine I asked you to put points into a square or a cube such that they are uniformly distributed. Okay, and Sobol gives you basically an algorithm for that. So it's the discrete measure, that means are points. So each of these points lie then in a sphere. I guess if you think about a 2- and 3-dimensional case, this is a trivial problem because you just put each point on a Cartesian grid. But if you then think about higher dimension, and here we're talking about dimension 100, then of course, if you use the Cartesian grid, the whole number of points would go exponentially. So that's not really an option. So you can use Sobol points. They don't scale exponentially, and they are better than just random numbers. And so this is why we use them. Very, very good method. And each of these points reproduce an answer. And then we take this answer and then further adjust this by a local optimization algorithm. In this case, we use Hooke-Chiefs algorithm. We take the top 3 Sobol points and then do Hooke-Chiefs. Here we also vary the dispersion ratio. We then do 2 rounds of Sobol points, And here you see sort of the three best ones that we achieve. In the first instance, this is the starting point. This is the value of optimization of the optimization function. And you see here ignition delay and flame speed. And you see that the model that we compare it to is actually at this stage much better. But then in the second step, we continue with another sensitivity analysis and with a smaller set of reactions. And then we arrive at this result, which is significantly better than the model in the literature. Now, you have to understand that this group, Lin et al., they're actually from NUS, it's just across the road from where I'm sitting now. This was a PhD student who spent half a year doing this, okay? And this process took us around 100 CPU hours. Okay, and here you see the results for the ignition delay time. Okay, so the red ones is our work. You see the hand calibrated mechanism was of course not quite good, but if you look at then at the laminar flame speed, you can see that the automated auto calibration outperforms the student. Right, and this is what it looks when you just write out each elementary reaction, and that is now part of the knowledge graph. Okay. Right, so hopefully I've convinced you that there is something to be gained if you use the knowledge graph, ontologies, and the agent framework to automate chemical model development. But there are other use cases. So one thing that we want to do now is we want to create agent access through Marie. I mean, before we just looked at properties, but now we want to ask questions. And then Marie, instead of trying to find a piece of information in the knowledge graph, starts an agent. And we have developed the quantitative structure activity relationship agent. So this one here, so this is an agent that for a given organic molecule, we calculate the power conversion efficiency. Okay, and this is sort of the classic specific data set in the literature. One is called V15, and there is another database called CEPDP, and so we have developed a number of machine learning algorithms to then fit these results. So basically we have now an agent that for a given molecule, it tells us something about the power conversion efficiency. And we are just about to include this into Marie, so watch the space. In a few weeks, there will be a new preprint where we show this. And then we are also working on lab automation. So here, this is collaborative work with Professor Alexei Lapkin. So we have a platform-based approach for a lab robot. So we have functional components, ad hoc data representation, and different ways of data exchange. And we want to propose a dynamic knowledge graph. So we want to pull that into Marie, if you want. Okay. So how do we do that? So we start with the real world. Okay. Here you see sort of the hardware elements of the experiment. Okay. And then we instantiate each of the components here of that experiment, okay, and develop sort of the agent network that works on these individual components, okay. So we have the execution agent that basically gives instructions to pump, reactor, and HPLC. We have a design of experiment agent that tells us what experiments we want to do. okay, and that would communicate to the instances, the sort of the digital twins here. And there's also a monitor agent and a post-process agent. Right, and then so the execution agent gives instruction to pump reactor, and the flow rate, temperature, chromatograms, they go back into the knowledge graph and triggers the whole process here. So that is work in progress. Hopefully, not too distant future, we will be able to show this. And here, finally, sort of a real hardcore example for interoperability. Okay, you've seen that we can do chemical models for combustion, and now we push that to the extreme. And what you see here is a creation of a virtual sensor across different domains. So imagine we want to know what is the emissions caused by marine traffic in front of Marina Bay Hotel in Singapore. And the Marina Bay Hotel was the beautiful picture of this surfboat on three pillars I showed you earlier. So how does it work? So in the first instance, you have to pull the real world into the knowledge graph. So you need to know what a ship is. So you need an ontology for ships. If you want to know how the emissions affect people in Marina Bay Sands Hotel, you need to know something about the weather, the wind, whether it's raining, and so on. But you also need to represent buildings, and that's done with OntoCity GML. We have the weather ontology, and then you need to represent the combustion process in ships, in the engine, and that is done with OntoPESScan, that gives us the engine, and then OntoKin gives us the chemical model, and SRM is an engine simulation agent, and that would then pass on its information into the exhaust of the ship, and that in turn, this exhaust is affected by the dispersion, which is done by this ADMS agent that uses weather, the position of the ship, and of course also the surface information to calculate the dispersion into the soft sensor. So what I show you here is a 24-hour simulation of real ship position. The black dots are ship position. Here you can see the Marina Bay Sands Hotel, and you can see different pollutants. These are unburned hydrocarbons, but there are also NOx, PM2.5, PM10, and you see over the different times that the wind changes, ship position change, and you can sort of place the virtual center somewhere here and basically calculate whatever the dispersion passes here on. And here, for example, wind comes different direction, and that's of course good news for the people in the hotel. And with that, I would like to close my talk. I'd like to thank all the collaborators, the team. This is CMCL, my Como group at Cambridge, and the CARES people. Would like to thank you for listening to me. And that's the end.